Hello and welcome to week 6 of MATH375. So last week we started with the problem of pricing and hedging. We defined our market, which is a two-asset market. And one of the reasons that we are considering only the two-asset market is because most of what we will say with regards to the two-asset market remains valid even for the multi-asset market. However, not everything. There are some problems that appear in the multi-asset market which do not appear in the case of the two-asset market. Nevertheless, this is the market that we are considering. And we said that the main problem in this market is how to price a derivative security, which is a contract whose value depends upon some underlying asset. So for the moment, we are considering contracts which are fully defined in terms of their terminal value. So we know what is the value of the contract, let's say at time capital T. So we would like to know what is the price of such contract at some earlier time. According to the arbitrage pricing theory, one should price a contract in such a way that if you introduce such a contract into a market, it will not create arbitrage opportunities. In other words, arbitrage opportunities of making a riskless profit. Two claims that we made last week were that in our two-asset market, there does not exist an arbitrage opportunity. In other words, you cannot construct a self-financing portfolio, which is an arbitrage. And the second claim that we made is that there exists a hedging strategy for our derivative security. In other words, a certain backward stochastic differential equation has a solution. So these are the two claims that we made last week. And this week we will show that that is indeed so. Okay, so let us begin. So section 2.3 is on the change of measure and Kirsanov's theorem. Before we begin in this section, let me remind you that in chapter 1, we considered the problem of changing the measure. We talked about what are equivalent probability measures. And in particular, we had an example of a random variable, which was not standard normal. However, after introducing a new probability measure, it became standard normal. In this section, we will consider a more general situation, namely, we will have a process which is not a Brownian motion. However, after introducing a new probability measure, it becomes a standard Brownian motion. And this is precisely the Kirsanov's theorem. And why is important? Why will we do the change of measure? It will become clear in the following two sections. However, in this section, we will simply do let's say, the math of changing the measure. And in the sections that follow, you will see why are we doing this. So we will show in this section that the discounted stock price and the discounted wealth process are martingales under a particular probability measure. First of all, what do we mean by a discounted stock? Well, we mean precisely this that you see here. So if you divide the stock with a bank account, or you can call it, you multiply it with a certain discount process, what you obtain is the discounted stock. Similarly, you have for the discounted wealth process. So in general, in pricing, which asset you use for discounting actually depends on a particular application. However, in this case, since we only have two assets, we will use the bank account to do the discounting, which is also quite typical. Now, the discount process, as is clear from here, is simply 1 over the bank account. In other words, the differential of the discount process is minus R dt. Later, I think in next week, when we talk about the risk neutral pricing formula, this relation will be useful. However, this is very straightforward. So in other words, this product can be written like this. Okay, so these are the discount processes. And as you can see here, we are dealing with the product of two processes. And we are interested to know what is the differential of the product of two processes. We can use Ito's formula. However, a more useful tool is a special case, actually, of a multidimensional Ito formula called the Ito's product rule. So if you remember from calculus, if you had the product of two functions, and then you had the product rule to find the derivative of the product of two functions. Well, even if if we have a product of stochastic processes, then we have the so-called Ito's product rule, which is more general than the product rule from calculus. Okay, so that is the tool that we will need in order to find the differentials of these products. Okay, so what is the Ito's product rule? Well, consider two Ito processes, which are processes of this form. And suppose that we would like to know what is the differential of the product. Well, according to Ito's product rule, this part is the same as in ordinary calculus, namely the differential of x1 times x2 plus x1 times the differential of x2. However, we also have the third term, which is the product of these two differentials. Okay, so the proof of this result follows directly from the Ito's formula, but for the multidimensional case. So keep in mind here now, the dimension of the Ito process is 2. So we have two processes. Also, I hope you can notice that when you form these products, you will have to deal with products of the following type, namely dt times dt, dt times dw, and dw times dw. Now, what are the values of such products? Well, we haven't actually precisely defined these terms. So that is why what we will do is what is, let's say, a convention. So a certain rule that we will use, which is not mathematically precise. However, if you use it, you make no mistake. So let us see what that is. So we will use the following convention when we, or rule, let's say, rule, when we apply Ito's formula. Whenever we have a dt squared, we will take this as 0. Whenever we have dt times dw, we will take this as 0 as well. However, if we have dw squared, we cannot take this as 0, but instead we will take it as dt. What is the intuition behind this? Well, dt is already a very small quantity, or a very small quantity. If you square that, that becomes even smaller. So it is reasonable to take it as 0. Also, dt times dw is, we can take it as 0 because the expected value of this is 0. However, the expected value of this is not 0, but let's say intuitively or approximately, we can take it as dt. So if you think of dw as very, very small increment, that justifies these relations. Nevertheless, for our purposes, the point is that whenever we use this rule in our derivations, we make no mistake, and the derivation is actually rigorous in the sense that it follows from Ito's lemma. Okay, so if we apply this rule in the previous, so in here, so we apply this rule here, then another version of Ito's product rule looks like this. So please always be careful when you apply Ito's product rule, because in addition to your ordinary product rule, you have this third term. But also, you see, if one of the Ito processes does not have a dw term, in other words, either sigma 1 or sigma 2 is 0, then this disappears, and you have your ordinary Ito's product. You have the ordinary product rule with regards to differentiation. Okay, so now we would like to find what is the differential of the discounted stock. Just to remind you from last week, this was the differential equation for the stock price. And we would like to know what is the differential of this product. Well, we apply Ito's product rule. However, keep in mind that the differential of the discount process does not have a DW term. In other words, Ito's product rule is simply our ordinary product rule. So it is the differential of d times s plus d times the differential of s. If we substitute the differentials of these two processes, you get this expression. Now, here what we have done is we have taken the process d and s as a common factor, but we have also taken sigma. If you do this, you can write this relation into this if this theta is defined in this way. So theta t is an important quantity, an important process which we will use, and it is called the market price of risk. Market price of risk, and we will see its use in a moment. Okay, so we have introduced Ito's product rule. We have seen its application in finding the differential of a discounted stock. Now let us see what is this Kirsanov's theorem. Okay, so let us go through the theorem and then I will make a comment on it. But before that, please keep in mind that we are given a probability measure P and a Brownian motion W. So we know this. Kirsanov's theorem shows us how to construct another motion and another process which is also a Brownian motion. Okay, so let this alpha t be an adapted process and define the process Z alpha like this. The random variable Z alpha as Z alpha capital T. And let us define another process in this way. So please pay attention here that this is a Brownian motion that we already have, plus the integral of this process alpha. So this process alpha that appears here is used to define this Z. So if we add these two, we get another process. Now this process in general is not a Brownian motion under the probability measure P. Kirsanov's theorem shows us a way of constructing a probability measure under which this is a Brownian motion. There is another technical condition which we will assume that always holds in our situation. Now, if that is the case, then it can be shown that the expected value of this random variable is 1. Now, if you remember from chapter 1, we can use this random variable to construct a new probability measure in this way. So if we define this set function in this way, then this is indeed a probability measure. And since Z alpha is strictly positive, this probability measure is equivalent with this one. However, not only this, the process W alpha t under this probability measure is a standard Brownian motion. Okay, so and this is the Kirsanov's theorem. Okay, and it is very useful for our purposes, as we will show now. So we will apply Kirsanov's theorem in our market in a way that instead of alpha, we will use this market price of risk process. So let us do that. So if we use theta t instead of alpha t, then we define this process zt in this way. So as you can see, using the theta, and in particular this random variable and this probability measure, which we are denoting by p tilde, then by Kirsanov's theorem, the process Wt plus the integral of theta is another process which under this new probability measure is a Brownian motion. If we write this in the differential form, you can see that now this term, which we have encountered in the case of the discounted stock, is actually the differential of this process. In other words, we can write the equation for the discounted stock in this way, which after you integrate from both sides look like this. S0 is a constant. This is a stochastic integral under this measure, P tilde. So in other words, indeed, the discounted stock, since it is a constant plus a martingale, is itself a martingale under this new probability measure. And that is why P tilde is also called the martingale measure. The probability measure P tilde is also called the risk-neutral probability measure. Let us give one reason why that is the case. So we saw the equation for the discounted stock under this new probability measure. However, what is the equation of the stock itself under this measure? Well, this is the equation of the stock. However, instead of the dW, we have substituted this expression, okay? Which actually, if you put this term and this term together, it reduces to this. Now this looks, if you compare this equation for the stock with the original equation for the stock in terms of Brownian motion W, you will see that the only difference is, well, not only one difference, one of the differences is that this term here. So in the original equation, we had the mu s, and of course here W. However, after the change of measure, this has become R times S, and here we have W tilde. The coefficient here is usually called the expected rate of return. And as you can see, the expected rate of the return of the stock under this measure is the same as the expected rate of return of the bank account. It is the interest rate. So regardless of the uncertainty, in other words, or neutral towards the uncertainty, the asset has the same expected rate of return. Okay, so this is one of the reasons why another name for this probability measure, P tilde, is the risk-neutral probability measure. Now we have done this, we have considered equations of this type last week, and we know how to solve them. A particularly important case is when these coefficients R and sigma are constant, and the solution is given like this. I'm sure that all of you can recognize a process of this form because we have done several examples, and as you can see, the picture is emerging gradually. Why did I ask you to do certain calculations with random variables of this type? Because this is actually the stock price. And what you have calculated is actually the price of a derivative security. Okay, to summarize, we have introduced two results from stochastic analysis, namely Ito's product rule and Kirsanov's theorem. Using those, we have shown that the discounted stock price is a martingale under the risk-neutral probability measure. Let us show the same for the discounted wealth process. So just to remind you that the wealth of the investor who is using a self-financing portfolio looks like this. And from the very definition of what is the wealth of the investor, we have this relation, from which we immediately get this. Now let us substitute the differentials of the bank account and of the stock into this equation. You get precisely this. If you substitute this relation into here, so instead of, as you can see, VBT times BT, if you substitute this, you get the second relation. And from here, if you take VS and S as a common factor, sigma as well, you end up with this. Now, as you can see, this is nothing but the differential of this process W tilde T, which is a Brownian motion under the risk-neutral probability measure. Please note that this is the differential of the wealth, not the differential of the discounted wealth. And the effect or the purpose of doing the discounting is actually to get rid of this term here, as you will see. Now, what we will do next, you will find what is the differential of the discounted wealth. And as you can see, this term actually will cancel. So again, Pareto's product rule, the differential of the product looks like this. Since the equation for D of discount, for the differential of the discounted process, does not have a dW term, this thing here is 0. If you substitute the differentials for the discount process and for the wealth equations in here, you get this. As you can see now, this term here and this term here cancel, and you get simply this. If you integrate both sides from 0 to t, you get this expression, which clearly shows that the discounted wealth is a constant plus a stochastic integral. Now, the stochastic integral is a martingale under this new probability measure. If you add a constant to a martingale, it remains a martingale. That is why the discounted wealth is a martingale. So again, to summarize, we have shown here that under a particular measure, the discounted stock and the discounted wealth are martingales. Now let us address the first claim that we made last week, namely that in our two-asset market, there are no arbitrage opportunities. In other words, it's not possible to construct a self-financing portfolio. Let us show this using precisely the risk-neutral probability measure. The following result is quite important, and it applies not only to the case of two-asset market, but even to multidimensional market with markets with more than two assets, in other words. And the result is actually given in terms of the risk-neutral probability measure. So this is called the first fundamental theorem of asset pricing. Let us read it first, and then I will make a comment. So if a market model has a risk-neutral probability measure, then it does not admit arbitrage. So if you have a market model, whether in the case of two assets or many assets, and if you can find a probability measure under which the discounted assets are all martingales, then in that market, there are no arbitrage opportunities. So if we apply this theorem to our case, we already found out that in our two-asset market, there exists a probability measure under which the discounted assets are martingales, which means by this theorem, there are no arbitrage opportunities. Okay, so this is just the first claim of last week. You have the proof here. The proof is not difficult. I have given some more details that you can find in Shrieve's book. So I will leave this for you to read. I think it is a nice, simple proof. And just be aware that although in our market of two assets, there are no arbitrage opportunities, in general, in multi-asset markets, there are arbitrage opportunities. And we have actually illustrated this in last week's tutorial. Okay, now we turn to the second claim that we made last week, namely that there exists a hedging strategy. Okay, just to remind you, last week we considered this equation. So just keep in mind, this is our self-financing portfolio. However, instead of specifying the initial value, we specify the terminal value because X was the terminal payoff of our derivative security, and we wanted to know if there exists a VBT, VST, and Y of t that satisfy this equation. In other words, does there exist a hedging strategy for our derivative security? These equations are called backward stochastic differential equations. And these appear in many areas of mathematics, not only in mathematical finance. And these have been studied extensively in the past 30 years. Okay, so the question of existence of solution is what is the main problem of this subject. And that is what we will show. So in this section, we will actually show that this equation does have a solution. In other words, there exists a hedging strategy. Okay, so this equation so this is, as you can see, our self-financing portfolio. After you do the discounting and the change of measure, as we did in the previous section, this equation becomes this. However, keep in mind that the terminal condition, so in other words, we require this to be equal to this P almost surely, P tilde almost surely, because we are working under this probability measure. So keep in mind, this is the Brownian motion under this measure. So these two problems are equivalent in the sense that the solution of one immediately gives the solution to the other. And just to remind you, when we talked very early on in this module about the change of measure, I said that we would like that certain events that happen for certain in our mathematical world to hold true even in the real world. Otherwise, there would not be much point of doing of our method. Our method would not work. And that is precisely the situation here. As you can see, this is the equation under the probability measure P tilde, which is a mathematical construct. Okay, so this is not the probability measure of the real world. So this is something that we have constructed. So if this equation holds under this measure, we would like the same to hold true also in the real world under the probability measure P. So in other words, we would like this condition to hold true. This will be true only if both P tilde and P are equivalent, which is indeed the case. So this is why the equivalence of these two probability measures is important. Okay, so once we know that these two problems are equivalent, let us focus in finding the solution to this. In other words, let us see if there exists a process VST and a process Y of t such that this relation holds. How should we prove this? Well, we will use a certain version of the martingale representation theorem. Okay, so let us do it step by step. So suppose that we are given a random variable x, which is an F capital T measurable random variable, which, as you know, represents the terminal payoff of a derivative security. Suppose that we are given this random variable. Now we will define a process, particular process, using that. However, before we define that, we will have to restrict the set of these random variables x as follows. And these restrictions, that you can see here, actually comes from the martingale representation theorem. Let me remind you first what was the martingale representation theorem. So if you have a martingale MT, which we will assume to be a square integrable, and it is a martingale under this P tilde, then there exists a process gamma t, which is adapted to the filtration Ft. And remember, Ft was the filtration generated by the Brownian motion Wt. So there exists such a process so that you can write or represent this martingale as a stochastic integral. So this was the martingale representation theorem. Now, for a random variable x which satisfies this condition, we will define the process xt in this form. Okay, it will become clear in a moment why are we defining this in this form. And the reason is actually because d times x is actually a martingale. Okay, so d times this process x of t is actually a martingale. And in other words, we can write it in this form. So let us do that. Let us first show that the process defined in this way is a martingale. As you can see, this is a conditional expectation with respect to ft, which means that the process is certainly adapted to the filtration. We require square integrability rather than simply integrability, which means that the integrability also holds. And all we need to do is to check the martingale property holds. Okay, and that also holds. So, as you know, we take the conditional expectation of something in the future based on the present. If you substitute the definition of this in here, you get this relation. Applying the Tower property, this reduces to this, which is just this. So indeed, this process this process dt times x of t is a martingale. If it is a martingale, there exists a process gamma through which we can represent it like this. Okay, so this is the first step. Now, let me remind you what was the discounted wealth process in an integral form. It looked like this. As you can see, if we compare these two equations, they are very similar. They have a constant and they have a stochastic integral. Now, if y of 0 is precisely x of 0, and if Vs is such that the integrand of both integrals are equal, then this expression will be the same as this one. However, since you see you have dt here and dt here, this immediately means that y of t will be equal to x of t. Okay, and please don't forget that xt at time capital T is precisely x, or the payoff of the derivative security, which means that y of t, y of capital T, will also be equal to x. So in other words, this actually proves the existence of solutions. So this actually proves the existence of Vs and the existence of y immediately by simply comparing these two. And that's it, really. So if you compare those two, you will have yt is equal to xt. If you ensure that y0 is equal to x0, and if you ensure that Vs has precisely this form. So this proves our second claim that we made last week, namely the existence of the hedging strategy. Now, Vs of t is the hedging strategy for the stock. So in other words, there should be actually a capital S rather than small s, but never mind. Vs of t is actually the number of shares that an investor must hold at each time t in order to have at time capital T of this relation. However, what is the number of shares in the bank account? Well, we find it from this relation. This relation holds for every t. And from this, you find VBT immediately. So in other words, now we indeed have, we know what is the number of shares that we should have in the stock and the number of shares that we should have in a bank account in order to hedge our position. Or in other words, in order to guarantee that this holds here. Okay, one final comment, well, a couple of final comments that I would like to make is that the martingale representation theorem tells us that this process gamma exists, but it does not give us a constructive way of finding this gamma. You have seen some examples last week in the tutorial, how to find the gamma, and there are a few more examples this week. And my second comment is that if you have a market in which every derivative security from a certain family, from a certain set, can be hedged, such a market is called complete. Clearly, in this case, our two-asset market is complete in a certain sense. Okay, so all the random variables that satisfy the conditions, all the derivative securities that satisfy the conditions of this section can be hedged. So in that sense, our market is complete. However, don't forget that there are incomplete markets. So markets where not every derivative security can be hedged. This is a situation where you have, let's say, more than one Brownian motion driving the assets. So as you know, here we have one stock, but also one Brownian motion. But those are problems that we will not consider in this chapter. Okay, so thanks for your attention. That will be it for this week.